Okay, so here we are. Run npm run test watch, so this thing gets started off. And it's going slow because I'm running a bajillion things at once. 250 pending, 0 passing. That's always a great way to start the day, right? So we will enable the Lexer spec, and we will actually also focus it. I hope you are using this for your own sanity's sake. My computer is slowing down like crazy right now. Can y'all still see things are going okay here? Okay. So I'll make this a little larger temporarily so we can see the context. It's now showing 0 passing, 3 failing. So I turned on the Lexer spec. There's 3 if blocks. And what actually happens here? We pass a string, an empty string, into the Lex function, and it should be an array of no tokens. Well, we can pass that trivially just with return 0. Like, we don't even have to do an if check to pass the first one. We will have to, but we don't to actually pass it. Now, of course, I know that what I'm really trying to say is if there is no input string, then return 0. And that, of course, passes the exact same number of specs, but it does so in a more future-proof way. Converts ham to an array of 1 word token. So I pass the string ham into here. That's input string. And the tokens should be this array containing an object, and the object would be type word value ham. So if there is an input string, one way I can do this is I could simply say return an array. Again, sort of acting naive here. Type is word or quord. There we go. And value is, I could hard code it as ham. That does pass the second spec here. But naturally I know, well, I'm just not even paying attention to the input string. I know ham came from the input string. It's what was passed in here. So I'll just set it directly as a literal value. And the other thing is there's going to be multiple things. So I have ham and cheese on rye. There should be 5 words here. Ham and cheese on rye. So now I can't hard code in a single object. I have to have an object for every one of these. And that's a perfect example of mapping. The other thing that I'm doing is I'm ignoring white space. So that's a good example of splitting. If I split on space and I map the resulting words into objects, I'll get what I want. So we'll do input string, split on space, creates an array of words. I want to take every word, which is a word string. It's just the string like ham and I want to construct an object whose type is word. We end up not using that at all in this phase of the workshop, but I just wanted you to get used to it. And the value is going to be that particular word. And I can get rid of this return. And I'm missing something, which is an unexpected token because, arrow functions. This is a tricky one. So when I have a arrow function and I want to return an object, if I just use brackets, it thinks it's a function body. Speaking of ambiguous grammars, it doesn't know that that could be an object literal that I'm trying to make. But if I add parens, now our lovely JavaScript compiler is capable of disambiguating between function bodies versus object literals in parentheses. So this is the kind of stuff that now that you know a little bit more about parsing, you know, somebody had to go and code these kinds of rules. Anyway, this is now passing the Lex. So I wanted the first Lexer to be almost, you know, like mildly fun, a couple of gotchas here and there, but nothing crazy, so that you could get into parsing as soon as possible. Are there any questions about this code before we move on? Okay. One thing that I might do if I wanted to be kind of fancy is, I'll just show you quickly. This isn't really going to be an improvement. It's just going to be an alternative style. Right now I have a function body with an if. I could just do that as a ternary. So I check, is there no input string? And if that's true, then I return implicitly an empty array. Otherwise, I implicitly return the split string, and I can format this document using Prettier to make sure that it lines up correctly. It decides I'm going to put it like that. ESLint doesn't like this. ESLint doesn't like arrows used with negations and turn arrays. It's like nobody's going to understand that. But so now I have a war between ESLint, which complains about it, and Prettier, which strips away the parens. So is this better? Probably not. Just kind of like showing you multiple styles. Let's go back to what we had. Okay, we're passing that. We can remove the only from this, leave it active, close the lexer, move on to the parser. I like to do the split screen. And let's activate. So right now, parse bread is X described. Well, we'll say describe only this. And I'm also going to use Command K, Command 0 to fold everything down, and then selectively open just parse bread. So I can sort of keep my focus very narrow and tight here. Code folding, I think, is a very underused feature of editors. Okay, so our first thing is parsing bread and then filling and more fillings, sandwich, and finally just parse. And I went from leaf up to the root because if you parse just a leaf, all you get back out is a single tree node. If you parse something that's a parent of leaves, you'll get not only the node you're building, but a bunch of children which are nodes. And the further up the hierarchy you get, the more you get recursion building nodes that have nodes that have nodes that have nodes. And it's very difficult to reason about and think from the top down sometimes. So I decided to orient this bottom up. Yes. Yeah, I think it is insofar as if I am ever doing anything recursive, the very first thing I write down is the base case. Because if I don't even know what the base case is, I have no chance of figuring out how to solve the recursion part. If I'm writing, I'm going to show everybody like Haskell every time that anybody talks to me, but it's just how I do these days. If I'm writing something like, so there's already a sum function for lists in Haskell. So if I sum 1, 2, 3, I got 6. But if I was writing this for myself, I would say, okay, well, what's the base case for the sum function? If I give it a sum of an empty array, it should be 0. And if I give it a sum of some array that starts with a value and then it has a bunch of other values, and it might be the empty array, it's going to be x plus the sum of that other array. This is not an array, it's a list, but same idea. And now I just made my own sum function, which in theory still works. And if I give it an empty array, it gives me back 0. So I always, personally, if I'm writing something recursive, I start with the base case because it's easy to reason about the base case and you need it for the recursion to work in the first place. You can't start with the recursion and then see it work and say, oh, now I'll add the base case. That's impossible. But you can see the base case work and then build recursion on top of it. Does that make sense? Glad to hear it. Okay, so parsing bread, I gave you most of it, and your task was to fill in these two things. So let's look at the examples of what's happening here. We pass the string rye in to our lexer and get back a bunch of tokens. We know that the tokens are going to be an array of objects which have .type as word and .value in this case is rye. So token 0, this first token, has .value is rye. If we open up our first spec, this was copy pasted for every single suite. All it checks up here in this verify function is that the result is an object, that it has .parseTree and .remaining tokens, and that .parseTree is an object and .remaining tokens is an array. In other words, it's just formalizing and checking this function signature right here. Every single one of these functions says, give me a list of tokens, I'll give you a tree and another list of tokens. They all say that, except for the bottom one, parse. So that's what I'm doing. I'm returning a tree and some tokens. And what tree am I supposed to build? Well, we keep going and looking at our specs here, and it wants a bread node. This is a weird workshop. It's not trying to make people hungry, but it had that effect, I think. So it wants a bread node that has .type is bread and .child literal is the string rye. So this is going to be an object. Type is bread. And child literal, again, I could plug it in as rye, but I see that rye is this variable. It's parameterized. It's something that switches and changes depending on what's passed in. So if the next value is rye, I would put rye, but if the next value is wheat, I'll put wheat. So I'll just put next.value and know that it's always going to be correct, whatever it is. That just passed a spec. Yeah, we're passing a lot of the like copy-pasted ones, but now we look at consumes one token, leaving remaining, 0 remaining tokens. So the idea is we passed in this string rye. It got lexed into an array of one token, and that one token produced this tree node. So it's kind of like we used the token. We didn't actually modify the array or edit the array, but whoever calls parsebread, they're going to want to know, hey, parsebread, how many tokens did you require to build a bread node? And they're going to say, oh, I used one token, so you should start from the next token after that one, whatever you're going to do. The whole idea of this returning both a tree and a list of tokens is that you say which tokens were left over. And the tokens that were left over is everything but the first one in this case. That passed everything. So there's like 15 specs here, but 15 of them are, just kind of dotting the I's and crossing the T's. So you first see those 250 specs, but they actually go pretty quickly once you start typing. So far, so good? Okay. So we shall refold this. Yes, Gabriel. Mm-hmm. In terms of like, as you're building up the tree, you want to see what it looks like. Yeah, I think the very best version of that, one way you can do it is it's just like the workhorse debugging tool, of course, is console log. And I could say, whenever I'm going to console log, like especially something in the middle of many function calls, I want to have something really unique, which I command F and I can find it in my logs. So I'll say something like next in bread or something like that, which I know nobody else is logging, I hope, and I'll console log next. But now we have another problem, which is I could go look for it, but this function ran a lot of times. So I see all these times, it's like, well, which one corresponds to the one I want? That's another reason why describe.only ends up being very helpful. Or it.only. It's like, okay, I'm just going to run just this one spec. And I'll clear this before I do with Command K and save. And it runs a single spec. And it says next in bread is type word value rye. So being able to zero in on one spec at a time and use logs like this with annotations that are easy to find and identify. If all I did was log next, look how difficult it is for me to tell apart. Like, I don't necessarily, if this is in the middle of 500 other lines, I'm never going to find this and know what it refers to. So annotating your logs is a big thing. But the ultimate version is the built-in integrated node debugger. Now this can be tricky to set up sometimes, but what I'm going to do is I'm going to go right next to, I'm going to get rid of the console log. In fact, I'm going to delete it. And I'm going to go right next to, in the gutter, this area is called the gutter. You see how it creates this red dot? This is called a breakpoint. I'm going to turn on a breakpoint at this point in the function. And now I'm actually going to stop this, and I'm going to say start debugging, environment node. Now the problem is I was running this in the context of a Mocha test. So it is running, but I think it just ended because it just ran this file. Unfortunately, what I would love to show you, but I think it would take too much time for me to do right now, is how to set this up properly for a Mocha spec so that it runs Mocha for you and then dumps you out into the debug console at the right place. Why doesn't it want, okay, so there's this, and then there's a way of changing it so the program isn't just this, but it's add a configuration. Can I search for Mocha? Mocha tests. Ooh, that's good. Ah, so what does this do? This does run Mocha with these arguments. Run /test. No, I want to run source one dot sandwich slash star dot spec.js. Save. And maybe that will do it. So if I restart, attribute doesn't exist. Okay, I know I can set it up, but it would take me too long and I don't want to take away from the review. But what you get is a live editing view where I could just hover over things and it'll tell me what they currently are. And I can click next step and it'll go to the next line and it'll just do everything live. And instead of trying to console log, I could just kind of wander around and inspect things at my leisure. And that's where things get really nice. So I apologize I couldn't get it in under 5, but we got to move on. Okay, so where were we? We were going to run, let's go back to the terminal, make sure that our tests are running. And we were already parsing bread. Now we're going to parse fillings. So we parse this so we can fold that away. Come back over here and describe only parsing the fillings. And it can be annoying to like unfold, 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 but if I do in VSC, Command-Shift-P is the one command to roll them all. And here I can say unfold recursively, and everything in my current context will be unfolded, and all of its children will be unfolded, and so on and so forth. So all that gets opened up for my inspection. Parse filling, we give it ham and cheese and mustard separately as 3 separate tests. And each time we say, okay, parsing ham, parsing cheese, parsing mustard. What does it do? It returns an object with parse tree and remaining tokens, just like we had here. I'm just going to copy paste this, honestly. But it's not going to be rye or wheat. It's going to be ham or cheese or mustard. Now I could do this as if it's ham or if it's cheese or if it is mustard. And that'll work. And there might be some good reasons to do that. But I'll show you a nicer way in a second, at least more luxurious. So if it's ham or it's cheese or it's mustard, return a parse tree. But this type is not going to be bread. This is a filling token. So it builds a filling parse tree node, which has type filling. And it's got a child literal, which it does, and that's going to be a string. So I think I could just save this and boom, everything passes. Now, of course, I'm cheating. I wrote this, so I know where I'm going with this. But if we were just looking at the specs, and not even thinking too much about like the compilation, it tells us, okay, when I call this function, it should return an object with .parseTree and .remaining tokens. And the .parseTree should be an object with .type and .child literal. And The remaining tokens should be an empty array, but the original tokens should be an array with one thing. So the remaining tokens are probably going to be like, oh, I know I used one thing, so slice from that position onwards. So I don't even necessarily have to be thinking very deeply in terms of why am I doing any of this. You can get into this pattern of what is the spec asking me to do, and I'll just go do it, which is both good and bad. I think it's good because a lot of this kind of programming, imperative programming especially, you have to be able to just objectively say, what is the code doing, and how do I react to that? And learning to not make assumptions and just read what the code says and follow suit is a very important skill. On the other hand, I want you to think about what you're doing. I don't want it to be too rote and formulaic. So what are we actually doing in this parser file? In the parser, we've made tokens, and now we're trying to build a tree. And we're going to build the tree from the bottom up. It's called top-down parsing because we're actually going to end up calling these functions from other functions, and the root function we call is going to be parse everything. But it in turn is going to parse children, which parse grandchildren, which parse great-grandchildren. So we're building the great-grandchild parsers first, and all they do is say, hey, if you give me a token, I'll build the next node in the tree, and the node is going to tell you what part of this expression it's in. So we're constructing all these tree nodes, these objects that say what kind of thing they are and what value they wrap, and we move on to the hard one. This is definitely the one where it's like 3 challenges all collide in parse more fillings. So let's collapse this and remove the only and do that. Scribe.only, and I shall open this up and unfold recursively. So there's everything in parse more fillings. Now, I copied in the rules from the grammar. There's 2 rules for parse more fillings. Parse more fillings might be nothing. It's possible that there are no more fillings in this sandwich, that it just ends. The converse, the only other case that I'm allowed to do with more fillings is if it starts with the token and. If the first token in the list of tokens is the word and, then I know there's going to be another filling and maybe more fillings. So I'll start with the nothing node. And I think it does that right here. It's like if you parse an empty string, you should get back an object with the right shape. So I'll just, a priori, I'm just going to write return type. What kind of type does it want? It wants an epsilon type. Does it have any children? No, it's a nothing node, so it has no children. Sorry, nothing node. No kids for you. It represents that it didn't find anything here, so it would make no sense to say, but I did find some children. That's a contradiction. So if all I do is this, I think it passes like a couple specs accidentally or whatever. If I scroll up to here, it doesn't really pass anything that it wasn't already passing. So why is this failing? Because I'm returning a parse tree. See, this is why it's good to read the thing. Return an object with a tree and remaining tokens. So what I really want is parse tree is that thing I made, and remaining tokens is an empty array. I gotta remember every time that's what I'm returning. And it seems like it's farther along. I'm gonna hit Command K and save again, just so I can scroll to the top. Makes it easier for me. Okay, so parse more fillings, parsing the empty case now just works magically. Parsing on Rye almost works, but it consumes the wrong number of tokens. So if I come down here to where it says parse on Rye, well, wait, if I'm parsing more fillings and the next part of the string is on, this is also an epsilon node. That makes sense. But which tokens did I not use? I didn't use on and I didn't use Rye. When I was parsing the fillings, I said, oh, there's no fillings. You still have to go do something with on and with Rye. So if I do a nothing node, I just return the tokens as I found them. I say, I didn't use any tokens. You have to decide what to do with them. Just hit Command K, save. That works for onRye. Cool. So we're passing the empty string and the onRye string. The next one is and cheese. So this is the first time where it's like there's an actual extra filling to deal with. So I'm just going to copy paste this because I know it's the right shape, and then I can just modify the bits that are wrong. And what kind of, oh, and I've got a return. So now I need if-else logic. Like, how do I know that it's a nothing node versus this kind of node? What's the single distinguishing factor between those? Let's put it another way. Either I've got this or I've got this. If I look at the first token, what? Well, the first token, I don't know what it's going to be. There might not be a first token. The first token might be the word on. Who knows? But with this one, I know that if it begins with and, it's a filling that I have to follow it up with. So if this token, this next token is and, then I know it's got to be a different kind of node. It's got to be a more fillings node. But if it's not and, if it's anything but and, it's a nothing node. So I'll put that in if. If next dot value does not equal and, take all this, put it in there, format my document. It's all cleaned up. Now this is going to break. I clear this, save it, and things that were passing now are completely broken. It says before each hook, returns an object with parse tree and remaining tokens. What happened? Why did the hook break? Can't read value of undefined. Where would I go to look to find out what it's talking about? Ah, see, this was a trap. The trap was I presented you with an error, and you made a guess as to where to go look. If I wanted to be more systematic, where would I look that I know I should look? Yeah, so there are stack traces where it says, hey, on line 54, column 11 of parser, there was an error. So if I look exactly at line 54, oops, that's this thing I just made. Now, you may have immediately said like, well, okay, that's where it is. And I agree. It's not like you should always stop and check the stack trace if you know where it is and you're like, oh, I'm looking straight at the problem and I know what the problem is. Then yeah, of course, go ahead. But if you get stuck and you haven't actually followed the stack trace, that's where the fellows and the instructors are going to look at you and go, you got to debug better than that. So it tells us that can't read value of undefined. Where am I trying to read value? Next dot value on this line. That's what it's saying. Cannot read value of this thing here is undefined. Next is undefined. Why is next undefined? Because I had an empty string, so token 0 is nothing. That doesn't exist. So I'm not allowed to get a property of undefined, which means I need to use Boolean short circuiting to prevent that and say if there is no next, or if the next value isn't and. Another way of doing this is I could negate a positive predicate. I could say if the next value, if there is a next and the next value is and, then I should be doing this thing. And if that's not true, then do this instead. But I try to avoid negations as much as possible. That's not entirely true. The other way that I had it was really talking about if it's this case, but never mind if it's not that case, do this. This feels to me more like this logic is related to this case. And this is a bit of an art, like finding the balance with Booleans. One thing you can do that I encourage you to do is say like const no next equals there is no next, and const next is and, but then I don't get short-circuiting a laziness. So this would actually fail and bug, so I can't do it this way. So yep, this is about as good as I can think of off the top of my head. Okay, where did we leave off? We were in the middle of trying to parse and cheese. So and cheese, it's got to be parse tree and remaining tokens. It is. The type is going to be a filling, so I just changed this. The child literal is going to be something. But now look what I'm doing. I'm re-implementing logic that I've already implemented previously. I have a function that if I give it some tokens, it will parse a filling for me. It's called parse filling. So instead of starting to construct this filling node myself, I'm just going to use the function I already have that does that. Now, the first token is the word and. The second token is going to be a filling, or the second series of, starting from the second token is going to be a series of fillings. So I can't pass tokens in because the and word is the first word in that token stream, and fillings don't start with and. So again, I have to say, give me everything after the and put that into parse filling. But wait, I've gotten lost. I'm parsing more fillings. So I am going to have an object. Whoops, that's not what I'm trying to do. I'm going to have an object whose type is, I misread, I was on like the wrong area before, whose type is more fillings. That makes more sense. Either one way or another, it's a more fillings. And what do these things have? They've got dot child filling and dot child more fillings. So child filling is something, and child more fillings is something. And we'll put in here, this is what I was trying to get at before. I'm going to parse a filling. It's like hand it off to the parser that knows how to read tokens and turn it into a filling node. Don't do it yourself. Same thing with child more fillings. Well, this is going to be another more fillings. So I have to parse more fillings. And I'm going to pass in some tokens. This is starting to get a little tricky because how many tokens will parsing the filling take? Will it take one? I might go look at the grammar and logically prove to myself as a human that it does take one. But what if somebody adds a filling later that's the two words hot sauce? Now, if I parse a filling, it'll take up 2 tokens sometimes and 1 token other times. I might just add that to the workshop. So I cannot assume safely for all time that if I do something like this, that it's always going to be okay. If the grammar is allowed to be changed. If the grammar is set in stone, then sure, whatever. I don't know ahead of time how many tokens this filling is going to use up. But I can find out because this object has the tree and the remaining tokens after the filling has been parsed. Remember, that's what everything we keep returning is a tree and leftovers. A tree and leftovers. So when I call this function, I get a tree and I get leftovers. So that's this filling result. I could say filling result dot parse tree here. And that's the tree that I want to attach. And which tokens do I pass in here? Filling result dot remaining tokens. And I need a comma. And I still have a problem, which is this gives me what? What am I getting back from this function call? What am I getting back from all of the subparsers? A pair of two things. What are they? Yeah, a tree and the leftover tokens. So this is an object. I don't want it to be an object. I mean, I want it to be a JavaScript type object, but I want it to be a tree node. So I'm going to do the same thing up here. I'm going to say const more fillings result equals, call this function. And now this can be more fillings result dot parse tree. And finally, what are the remaining tokens? Well, it's not all the tokens because I used up a bunch constructing a filling and constructing even more fillings. And I have no idea how many more fillings like these tokens just took up. It could be 17 tokens that it just swallowed in constructing all those more fillings. But it tells me right here, which are the leftover tokens. So I could just use it. More filling result dot remaining tokens. Save, and everything passes. This was definitely the hardest part of Sandwich. You're dealing with the fact that unlike these ones, you don't just check to see like what's the next token. You also have to see if there is a next token, and if the token is and or not. If it's not and, you've got to not only parse a filling, but then use the remaining tokens to parse more fillings, and use the remaining tokens from that to say, hey, when I parsed this filling, this is what I left off with, or these more fillings. So it's this waterfall effect where each parser consumes some of the tokens. And I've got to properly thread that needle and indicate that. Mm-hmm. Yes. So here's an example of the actual rule in action. A more fillings. We know we're parsing something that we assume is more fillings. We know it starts with and, filling, and more fillings. So this is what we're starting with. We assume it's this. Well, I'm allowed to, and is just and, so I'm not going to even bother changing that. Whoops. But more fillings, what am I allowed to replace that with? Well, I'm allowed to replace it with and filling more fillings. So I can paste this in. And what am I allowed to replace more fillings with? Well, I'm allowed to replace it with and filling more fillings. So I can get a string that looks like this. But wait, there's a more fillings here. What am I allowed to replace that with? I can replace it with this. Do you see how the recursion is causing this infinite loop of it just keeps going and filling and filling and filling and filling? When would that ever stop? It would never stop if the only rule was more fillings is equal to and filling more fillings. That's an infinite loop. But if I'm allowed a choice, and the choice is, oh, and by the way, more fillings can be nothing, that's a way of stopping the chain and saying, okay, there's my terminal case. What is going on with my copy paste right now? So more fillings can be replaced with nada, zip, zero. Now, why do we use an object that has parse tree is an object with type epsilon as opposed to something like null or false? It's nice when everything in your data structure is the same thing, which here they're all objects, nested objects that have nested objects, and remaining tokens are arrays that contain nested objects. If some of the objects might be null and you have no way of finding out ahead of time, then everywhere you might try to go traverse the tree, now you need to say, if this part of the tree exists, then do something. If it doesn't exist, do something else. Null checks are like a virus in code. The moment something could be null, now you have to have if-else logic for that null aspect everywhere. And it just keeps propagating and infecting everything. Whereas if it's an object, you can always say like dot, like traverse on this part of the tree. And then the base case is, okay, there's like undefines or nulls or something like that. So in reality, does it matter for this exercise? No. It's just so that like every parse tree node is itself an object that has type. In theory, for the math expression compiler, it actually does matter quite a bit because there's two kinds of nothing. There's additive nothing, which is 0, and there's multiplicative nothing, which is 1. And they are not the same. So you could not use null and null because you actually do want to have two different kinds of nothing. Does that make sense? Well, let's look at an actual concrete string here. Say the string is ham and cheese and cheese and cheese on rye. So this is the filler. Whoops, this is the filler. This is and more fillings, which recursively consists of and filler and an and more more fillings, which recursively consists of and filler with more fillings, which recursively consists of and filler and nothing. There is no token or character that this corresponds to. It's that there is no and. The fact that there is no and means the more filling is empty. There's a more fillings epsilon node that gets plugged in here, but it doesn't represent a physical token. It represents the lack of a token. Maybe. And like here it's trivial because it always has an on, but maybe we would have a version of this where it could be on rye or it could be over rye. And maybe people change it over time or something. All we know from the grammar is that the two options are, look, it's either and filling, more filling, or it's nothing at all. So if it doesn't start with and, it must be nothing. Alrighty, so, sorry? Yes, that's beautiful. Exactly. The thing that the epsilon value represents is the empty string. So if you go say inside of a string, hello world, how are you? Where is the empty string? It's almost everywhere, right? I could say there's an empty string here between O and W. Like that's kind of true in a weird, deep mathematical sense. It's not normally how we think of things. Right. It's yeah. Exactly. Yes. And understanding these algebraic structures is a really nice thing to add to your toolkit as a developer, especially as a functional developer. Okay, so epsilon represents nothing, which means it doesn't have a concrete representation. It stands in for something that's the absence of something. We already talked about this, and now we're going to parse a sandwich. Getting really hungry over here, everybody. Let's get rid of this only. Shrink that. Go to parse sandwich. And I'll recursively unfold this. And I'll change the describe to the describe only. And let's look at the sandwich rule. There's only one sandwich rule. This is unique in our grammar. All the other ones have choices, right? We have this one could be rye or it could be wheat. Either way, we end up building a node that looks similar, but it has a different literal. This one's the same thing. It could be ham or cheese or mustard. We end up building nodes that look the same, except the literal value is shifted. This one's a much more obvious choice between two very different possibilities. Something or nothing. Sandwich, there's no choice. So there's going to be no if. Probably. Maybe when I'm done there is an if. But ahead of time, I'm not assuming there's going to be any if, because it just tells me what to do. Look, a sandwich consists of a filling, more fillings, the word on, and bread. Well, I've got a bunch of tokens. How do I know what the filling is? I call parse filling. And this is a filling result. It's the pair of the tree and the leftover tokens. Well, how do I know? I've got some leftover tokens. How do I know what the more fillings are? I've got a function. It takes in the leftover tokens from the previous step, and it gives me back a tree and even more leftover tokens. So next is, there's this word on. Well, that means whatever the tokens are, not final tokens, but next tokens, is the remaining tokens from the previous step, but skipping the next token, which is the word on. So I would do .slice one here. And finally, I've got some bread. Well, I've got a function that if I call parse bread and I give it a bunch of tokens, it gives me back a tree and whatever tokens I didn't use, which hopefully are empty. And if we were doing semantic analysis, we would have checks like, are the tokens empty? They ought to be empty at this point. We're not going to bother checking. So this has a tree, this has a tree, and this has a tree. And I want to return an object with 3 trees on it. So I'm going to return something that's got a parse tree, which has child filling, is the filling result dot parse tree. The child more fillings is the more fillings result parse tree. And the child bread property is the bread result parse tree. And I've broken something. Let's close this, save this, open it up, see what we're currently failing. Parse sandwich returns an object with parse tree and remaining tokens. It's nice to have that guardian angel saying, hey, you forgot the remaining tokens. Well, what are the remaining tokens? Ipso, like knowing logically how this grammar works, I could just assume that they're empty. But of course, what it actually is bread result dot remaining tokens, which should be an empty array. But it's better to just code it in so that whatever it is, it's correct. And we still have problems. Let's find out what those problems are. So build a sandwich parse tree node. This parse tree is supposed to have a type saying I am a sandwich. And everything passes. So this is the top-down recursive descent aspect of our recursive descent parser. Because what we actually end up calling is this function, which calls these other functions, some of which call themselves. And so it starts at the top, but it very quickly just calls these other functions, which do all the parsing for us. So that's this recursive descent. But even though we're descending through the function calls from the top down, the tree gets built from the bottom up. That's how recursion works in general. We hit a base case, such as this bottom node, like this ham node, which is just an object. It doesn't call any more parsers. That gets fed back up to here, and we plug it into this tree that we're building. Conversely, we go a bread node, that gets fed back up here, and we glue it into the tree at this point. We call more fillings parser, which might call more fillings, which might call more fillings, which might call more fillings, but eventually it hits an epsilon node, which is the base case of the recursive more fillings, is there are no more fillings. And then all those bits of tree that are a tree with a child, with a grandchild, with a great-grandchild, those get glued into my sandwich tree at this point of the trunk and the bifurcation. And I end up with this beautiful tree that has all the structure. And then there's this weird other function lying around. What's the difference between parse and parse sandwich? They both take an array of tokens, but parse sandwich is like one of these subparsers. It gives me back a tree and whatever tokens weren't used. I just want parse, which I give it a bunch of tokens, it gives me a tree. So I call parse I can't type with this delay. Parse sandwich of the tokens. And that gives me back an object with a tree and remaining tokens. So I just pluck off the tree from the result. Save, activates the spec. And yes, one passing. I don't know why it says one passing. Oh, one passing for parser. Yeah, that makes sense. Okay, so that is the entire parser, which I will now do Command K. No, I won't. I will do Command Shift P, unfold all. And we get all 482 lines of the sandwich parser spec and all 100 lines of the parser itself, which, by the way, like I very frequently in my own projects find that I test at a ratio of, for every line of source code, I've got at least 3, 4, 5 lines of test code. That's like not at all weird. Maybe more people should do it than they do, but it's like if you are going to thoroughly unit test your code, you end up with a lot of code. The generator is short. I'm going to take about 15 minutes to do it, but before we go move on with the generator, yeah, questions. I just wanted a function that if I give it tokens, it gives me a tree, the end. It's an arbitrary choice to have this function. I could just use parse sandwich, and wherever I go want to get the tree that I'm trying to parse, the whole point of parsing is to build a tree. That is the end goal. So wherever I would use parse sandwich, I'd have to remember to myself, oh, and then do dot parse tree off the end of it. That would be kind of annoying, and I'd probably forget sometimes. So I just build this nice little wrapper function that plucks it off for me. Yes. Yeah. Yeah, and another thing, by the way, this whole sandwich deal it's very silly. Not just because the example's silly, but because this is not a sufficiently complicated enough language to warrant needing a parser. The whole idea of like what happens in generator, which is like turn it into this shorthand, could be done in probably like 20 lines of vanilla JavaScript really easily, given the language. But you hit a tipping point where a language starts to be recursive enough and self-similar and tricky to tease apart where you need a parser to properly understand what's going on. Sandwich language is not that language. Math expressions are sufficiently complicated enough that you really can't get away without having a parser for them. So yes, all of this is to get you practice at building a parser, an Elixir, and a generator. And then if you go and you want to try the math expression one, it's the same thing over again, just twice as hard. But not really twice as hard. It's very similar. It's the same kind of thing over and over again. It's like return a tree and some tokens, return a tree and some tokens. Which tokens did I use? So I'd use those ones, etc. Let's do the generator. Ooh, that's not what I want. Okay, so I'm going to undo this xDescribe, and I'm going to turn it into a describe only. And I'm going to Command K that. And I gave you these two switch cases kind of off the bat as like, all you have to really think is, given a particular node type, what does it mean to turn a bread tree node back into a bread string? What does it mean to turn a bread tree node into the shorthand version? Code generation is just using the tree to construct a string. And these particular two examples, like, doesn't require a lot of complicated logic. So the original generator, the idea is now we have a tree. Well, here's a stupid thing we could do with it. We can use it to reconstruct the original string. So let's say that I pass a bread node that looks like this. It's got type bread and child literal as rye into this function as node. And because the node type is bread, I end up here. And I want to return a string that was whatever the original string was for this node. It's just node.child literal in this case. So I save that. Generator, when given a bread parse tree, returns the literal bread name. I noticed that my lexer is still, my parser still got something in here. Describe only. Oh no, that's what I want. That's the generator. I'll do a command F for only. There it is. Get rid of that. Save, close, refresh, clear, scroll. There we go. That's what I wanted. Generate original. When given a bread parse tree, returns the literal bread name. Okay. It's kind of almost embarrassing. How about when given a filling? A filling, it should also return the literal filling name. I think I could just copy paste this because both fillings and bread nodes have .child literal, which is just a literal string. So I shall, whoops. That passes as well. How about when given a nothing node? What is the string equivalent of nothing? We already talked about it, but somebody, yeah, empty string. Let's check that that works. I wish that the Mocha reporter by default cleared the screen before it spit everything back out. Yeah, that works. How about if there are more fillings? Now it starts to get a little bit trickier. So let's look at more fillings. What do more filling nodes have? They have a child filling, and they have more fillings, which might be nothing, or they might be something. And because of more filling, if it's an empty node, I already have the empty case, that's epsilon. So if I'm on the more fillings type, that's the non-empty version of more fillings. So I know it starts with the word and. Now I'm going to deliberately make a small mistake and we'll come back to it. It's going to start with the word and then it's going to have a filling. So the one I'm giving you in this example has .child filling, .child literal. But in theory, what I could just say is, look, this is recursive. I want the string version of this filling. I've got a function that I can pass filling nodes into, and it'll tell me what it is. Child filling. And then if I change how I want fillings to look, it'll just automatically work here as well because that's I'm using fillings here and I'm using fillings here. So if I change this logic and I decide fillings should really be prefaced with a thumbs up sign, it'll work everywhere. Likewise, I can recurse onto the more fillings, which might be an epsilon node or they might be truly more fillings. And that's child more fillings. And now, of course, I look at this and it's kind of ugly, like the line's pretty long. So I'm going to hit format and it actually lets it stay because without doing two up, it looks like that. I'm sort of surprised that prettier lets the line go that long. Oh, you know why it does? Because I have prettier ignore. Haha. If I take away that directive and I allow it to format my document, it does this, which I kind of don't like as much. I find that less appealing. So what I'm going to do is I'm just going to manually format it like this. return and plus, I'll use parens, and plus original plus original close paren, and now I've got a nice shorter line. Then there's sandwich. What does a sandwich consist of? Well, we know it's got a filling, it's got more fillings, it has the word on, and then it has bread. Say again? I did. So check this out. Given a more fillings partially returns the original string. It's not passing, but it seems like it should pass. Expected undefined. Oh, I have a. That's actually a different error from what I was expecting. Expected undefined to equal and cheese. It's generator spec 54. Okay, so generator spec 54 expects this string, which comes from calling the original on this particular tree. So child filling, I'll just double check that these things make sense. Child filling, child more filling. I've got the string and plus these two things, which should be okay. So now I'm actually debugging like totally legit for real, not sure what's going on. So I'm going to do an it.only. Really focus in here. Okay, so expected was space and space cheese. This is the error I expected to see. The actual was and cheese. I've been thinking so much in terms of tokens, I forgot the original string had white space. So if I pad out the and, now it passes. That is the error I put on purpose, but that's not the error I thought I saw in the terminal, but then it turned out to be the error. Yeah, going all over the map here. So that was my deliberate, like, I'm going to like not think about spaces. But now if I want to reconstruct the string, I have to start thinking about putting them back in. And by the way, this points out that what we have constructed with this sandwich compiler is not quite a concrete syntax tree. A concrete syntax tree, or CST, is different from an abstract syntax tree, or AST, in the following respect. A CST maintains every piece of information from the original string. That's the strictest interpretation of a CST. I think most people use a slightly less strict interpretation, which is what we're building is pretty much a CST. It maintains a lot of stuff, even stuff it doesn't necessarily need, like epsilon nodes in this case. An AST simplifies the tree to just the information that's necessary for your use case. So an abstract syntax tree says, I don't need to know all of the details about they used double quotes versus single quotes. I just need to know it's a string. That's an abstract syntax tree. If I want to pretty print, I don't really care about the existing white space. The way Prettier works is it parses your JavaScript into a tree, and then it reprints your JavaScript, but following its own rules. So I've got a string node. I'm going to use single quotes. Who cares what quotes you used? Oh, you had semicolons. I didn't even save that in the tree. I threw them out. If I'm pretty printing, if you tell me to put semicolons, I'll put semicolons at the end of every statement. But if you don't want semicolons, I'll just omit them. So Prettier itself is a beautiful example of parsing in action and code generation in action, compilation. Okay, where were we? Sandwich. Sandwiches have child filling, child more fillings, the on word, and child bread. So it's going to look like this. It's going to be, why doesn't, oh, because it's empty. Return the original version of node.child filling, which I could have copy pasted from above, but whatever. The original string of node.child more fillings. The word on spaced properly. And finally, the original version of node.child child bread. That is from my wife. I will hide it from, no. There we go. Sorry, private communication. Original child filling, child more fillings, child bread. That saves? Okay, good. Generate original works. Yay. Then we've got all these examples that we can test, and it goes through, and we're doing describe.only right now, aren't we, somewhere? Yeah, it.only. Get rid of that. Everything passes. Good. So ham and cheese on wheat is the same string. So it goes in and comes back out, and we've done an immense amount of work to have zero effect, which I always think is kind of like, Sisyphean in a way. It's like you slaved away to do absolutely nothing. But now, in order to at least have some payoff, even if it's not a lot of payoff in this workshop, the math expression has nice payoff, but it's longer. Nobody ever finished it. There's this shorthand thing that I invented, which is a sandwich is like the bread code in caps with parens surrounding the fillings as lowercase letters. Fine, we'll do it. So bread node is going to be the first letter capitalized. So it'll be node.child literal 0 to uppercase parens close. Save. And I want to run this spec, so let's get rid of the only on this, fold it down, get rid of the xdescribe, run just the spec. And what's actually passing, let's find out, save again. Currently nothing is. That's fine. So the examples are complete. So I didn't do it piecemeal for the shorthand. I just said, you've got the idea by now, figure out how to do it properly. So we'll just do everything. We'll do it all in one go. This is going to be the exact same thing, but it's not going to be to uppercase because fillings are just lowercase letters in this shorthand. Epsilon nodes are still the empty string, so that we can ignore. More fillings. More fillings. What does a more filling normally have? It's got the and keyword, which we're not including. It's got a filling and possibly more fillings. So we're going to call shorthand of node.child filling, get whatever that letter is, and we're going to glue it onto whatever the other fillings are, which is the shorthand of node.child more fillings. Once again, I've ended up with this kind of ugly line length, so I'll just manually do it since I disabled Prettier from operating on these switch cases. And it looks something like that. And sandwiches, what do sandwiches consist of? They start with a filling, so I call original. Oh, you know what they do? They start with the bread. So the normal sandwich, it has a bread. This is a beautiful example of like, now we can just start playing with the tree structure. The original version is it goes filling, then more fillings, then on, then bread. But I'm going to do bread and then parentheses, which weren't even in the original string, and then all of the fillings and more fillings. So this is going to be the bread. And I'm going to want like again, this kind of return statement. So I want the bread, which is uppercasing and initializing itself, plus, I guess I'll put it up here, open paren, plus the original, not the original, the shorthand. What am I doing? Nobody called me out. Everybody's tired. It's been a long day. Node, child. You're like, well, it must be, right, if he's typing it. Child filling, and the shorthand for node.child more fillings. And finally, it'll end in close parens. And I save that, and everything passes. And if I get rid of the describe only, and I just save that, 71 passing, 179 math specs to go. But there's a compile function here, which is a single compile spec that just says, hey, if you made all this stuff, it works now. So now it's 72 passing. And my sandwich compiler is complete. And not only is it complete in terms of specs, I can call it from the command line. npm run start sandwich ham and cheese and rye, and it's like, oh, that's an RHC. Hey, I built a program. The end. Okay. It is 6:11. I can stay for a short period for a couple more questions. They can be about specific technical code things. They could be more general questions, whatever you like. Anything? How are people feeling after this one? It's a big, long, challenging workshop. But I hope that I maybe imparted a little bit of interest in the subject to you all, that you were inspired to go read more and, keep trying and keep practicing. Like, we didn't even touch the math expression compiler. There's a solution code, which I put into Slack, but you might, now that you've seen the sandwich, you might just try, hey, let's see if I can finish the math on my own. I hope that you give it a shot, and you can always Slack me with questions. Good evening, everybody. Thanks for your attendance.